R-CADT, Research Center for Advanced Decision Technologies is pleased to invite you to participate in the Postgraduate Level Course, Electricity Sector, Enterprise-Wide Optimization, a different course in Advanced Optimization. HI operates as a knowledge factory in artificial intelligence and advanced mathematical modeling, focusing on artificial business management, autonomous AI that guarantees objective decisions, artificial brains, integrates organizational decisions based on neuroscience, enterprise-wide optimization systems, EWOS, customized AI that integrates multi-problem model systems, and high-complexity mathematical models, traditional models that are part of our artificial brains. The course covers the following artificial intelligence methodologies: predictive artificial intelligence, machine learning, framework, advanced probabilistic models, neural networks, support vector machine, and hybrid methods, Kalman filter, decision-making artificial intelligence, framework, economics and optimization, large-scale optimization methodologies, mathematical programming with equilibrium constraints, parallel optimization, real-time autonomous distributed optimization, and artificial brains. From the oil and gas course, we extract a independent testimony. I am proud to share that I have successfully completed a diploma program from Hypothalamus AI focused on leveraging mathematical modeling and AI for strategic decision-making in the oil and gas sector. I deeply appreciate Jesus Velasquez Bermudez's dedication and effort in delivering the training. I am confident the knowledge gained will greatly benefit my professional endeavors. Chemical Engineer, Staff Optimization Engineer, Saudi Aramco, Total Refining and Petrochemical Company, SATORP. RCADT and/or HI issues a certificate signed by the scientific coordinator, for which the student must participate in at least 20 conversation sessions. The instructor of the course is Engineer Jesus Maria Velasquez Bermudez, Ph.D., who, in 2024, won the Artificial Intelligence Award of the Industrial Engineering and Operations Management Society, IEOM. Hypothalamus Artificial Intelligence brings real-world electricity business optimization to academia, to teach the implementation of optimization systems across the enterprise. HI has established technology and commercial agreements with organizations committed to highly complex mathematical modeling, such as GAMS, General Algebraic Modeling System. GAMS supports HI courses by providing students with temporary licenses to use during the course. Then, the material that HI delivers in GAMS programs may be used by students. The support also includes 1 or 2 lectures given by GAMS, to present its optimization technologies. R-CADT, Research Center for Advanced Decision Technologies, is a division of Hypothalamus Artificial Intelligence Incorporated, USA, oriented to research, technological development and innovation, RAND+I, in high-complexity mathematical modeling, with an emphasis on optimization, whose mission is to bring its benefits to humanity, which involves enable professionals to successfully apply optimization technologies in their organizations, and be entrepreneurs and mentors of new companies, spin-offs, that bring the benefits of optimization technology to society. Currently, the central topic of RCADT's research is augmented artificial intelligence and more specifically the artificial brains. To fulfill its mission, RCADT has created a set of courses in advanced mathematical modeling that are aimed at supporting professionals interested in receiving applied training, at a cutting-edge level, based on the experience capitalized on more than 50 years executing engineering projects and development of analytical software. Parallel thinking. Like paper-based math, sequential math for single-processor computers is dead. As in the human brain, in the future only parallel mathematical thinking will be practical. The new analytics are autonomous, parallel, and distributed. Objective and structure. Vision. The material covered in the course covers 2 broad areas of applied mathematical programming: electricity systems and markets modeling, and implementation of enterprise-wide optimization systems. Vision. The course covers 2 broad areas of applied mathematical programming: electricity systems and markets modeling, and implementation of enterprise-wide optimization systems. Both topics are addressed from High's vision of multi-problem mathematical models, in which the development of computer solutions is oriented from the programming of algebraic formulas to the structuring of models, integrating the problems that make it up, as a Lego game. The student will learn about the main technologies for the implementation of mathematical programming algorithms and will learn to see them from this point of view, typical of Industry 4.0. But it is not a specialized course in algorithm implementation. Structure. The course is based on specialized academic activities aimed at training the participant in the main mathematical problems that must be solved in the strategic and tactical planning, operations scheduling, and process control of power systems and markets. The basic unit of the course is the virtual session with an average duration of 90 minutes each. To do this, the classes are recorded on videos, by artificial intelligence. Classes are grouped into modules that cover the electricity supply chain and the commercial markets. After watching the videos, students must attend face-to-face virtual sessions, in which the course teacher will clarify existing doubts. 2 conversations are held monthly. Students should submit their questions in advance. Objective. The course program is aimed at training professionals, at the graduate level, in applied mathematical modeling, taking advantage of the instructor's 50 years of experience in the area. The course is aimed at professionals who want to become applied professionals in highly complex mathematical modeling, with emphasis on the use of methodologies and technologies for the solution of large-scale optimization problems. It is also useful for graduate students who are pursuing theses or research projects related to optimization applied to complex problems. It encompasses the teaching of the theoretical foundations of large-scale optimization, with an emphasis on atomizing problems to solve them in parallel computers or computer networks. The objective is to present the integrated vision of real-time distributed optimization, RTDO, as the mathematical way to model the cyber-physical systems of Industry 4.0. It is characterized by the integration of multiple algorithms that continuously cooperate to solve the problems of a multi-agent system, independently using the parallel computers of the agents and sharing information to cooperatively achieve an optimal solution. This theory is constructed using the fundamental theories of partitioning and problem decomposition, Bender's, Lagrange, Dantzig-Wolff, cross-decomposition, and others. By the end of the course, the participant should be aware that future mathematical models will solve problems of more than a billion variables, or perhaps trillions. Objective. The course covers the following topics: next-generation analytics and advanced computing, parallel thinking for the partitioning and decomposition of complex systems, and implementation of power enterprises-wide optimization in the real world, specifically, Bender's partition theory, Lagrangian relaxation, Dantzig-Wolff decomposition, cross-decomposition, subrogate programming, and asynchronous parallel optimization, sliding optimization. Advanced concepts of artificial brains. For the different methodologies, examples of real-world problems and computer programs are presented, so that the student understands the application of what is taught. Aimed at professionals, engineers, data scientists, mathematicians, physicists, consultants, economists, software developers, etc., who require and/or wish to become experts in mathematical modeling, acquiring the knowledge to handle the state-of-the-art parallel and distributed analytical level, using mathematical programming intensively. This continuous training program strengthens the analytical skills and professional criteria of the participants, so that they can exercise, share and/or supervise, with propriety, the professional functions of this branch of knowledge, in accordance with the state-of-the-art of the methodologies and technologies that support the digital transformation of companies. The course is aimed entirely at the electricity sector, therefore, all the material will deal with this industry and other energy-related businesses. Obviously, those who get the most out of the course are mathematical modelers experts in the power industry. But executives, managers and engineers in the industry are trained to understand the present and future of artificial intelligence for decision-making, to structure and participate in projects of this science of the future. Artificial intelligence is accessible to everyone, but understanding its true scope requires proper training. High can teach knowledge, but it cannot create understanding. This is the responsibility of the student. Duration. The total duration of the course is 50 hours of training, divided into approximately 25 sessions of 90 minutes each session. The course is designed for the student to take 1 or 2 classes each week. However, the speed at which the course is carried out depends on the student. There is no class calendar. Start date of the virtual course. At any time. Classes are recorded using artificial intelligence. All videos are offered in English, and some of them in Spanish. Being on YouTube, all videos can be read in another language using the subtitle service, CC. Every 2 weeks, a discussion on a specific topic is held, which all students are welcome to attend. Material. The student receives a book in editing, draft version, with the material seen in the course, documents drafted especially for each of the sessions for some classes, the source codes of the mathematical models associated with the class will be distributed. Permanent access to all videos of the recordings of the class sessions. PDF copy of the presentations used to record the videos. Access to a paper's digital library with specialized documents on the topics covered in the course. Project. If the student wishes to carry out an advanced analytics project during the course, they can indicate this to the scientific director. If accepted, an advisory program on the project would be jointly defined between the R-CADT and the student. Artificial hypothalamus, mathematical programming 4.0 and autonomous real-time distributed optimization are part of the new dimension of mathematical programming. These ideas are at the core of the course. Artificial entrepreneurial brains rely on the development of parallel thinking, when a complex system must be analyzed. And reality is complex. The diagram presents the simultaneous evolution of 3 fundamental aspects in Industry 4.0. Information technologies, analytics and mathematics. The instructor of the course is Engineer Jesus Maria Velasquez Bermudez, Ph.D. Who is the creator of the artificial hypothalamus, the result of the integration of mathematical programming with artificial intelligence based on neuroscience. Most of the things and processes that humans use have been totally affected by technology, which has opened up to the human imagination producing previously unsuspected results. Mathematical modeling should not escape this process, starting from discovering the mathematical foundations that serve to establish the laws that govern physical, industrial, economic, biological, health, and social laws, and with them build mathematical models, and increasingly powerful calculation algorithms. Nowadays all knowledge and technology are available to develop a higher-level artificial intelligence, which emulates human intelligence in any type of human organization, and can be called the artificial hypothalamus of the organization. The power of today's technology is not in the mathematical calculations it allows to be performed, it is in the mathematical calculations we can imagine we can perform. The founder and chief scientist of HA is the creator of Optex, his most important technological work. The video. The history of Optex, the optimization expert system. From the simplex method to multi-problem models, Optex expertise meets artificial brains, moving toward mathematics-based general artificial intelligence. And the article Optex, where optimization expertise meets artificial brains. They present the history of Optex, which is the professional history of Jesus Velasquez Bermudez. Jesus Velasquez Bermudez in 1990 created Optex, Optimization Expert System, an optimization platform that was developed with a new vision of mathematical programming. To date, Optex has completed 34 years of continuous growth and updating. Proof of this is the current R+D plan that HI is developing to incorporate the latest achievements of AI, such as ChatGPT, to facilitate the dissemination of mathematical modeling in Industry 4.0, taking it to the level of people not specialized in the subject. You can find more information about Optex in the LinkedIn post. From simplex method to mathematics-based artificial general intelligence. The founder of HI has focused his scientific research on the development and incorporation of parallel optimization algorithms to Optex, the algorithms created are Primal Dual Subrogate Algorithm, PDS. Multi-Level Benders Partition, MBP. Generalized Stochastic Dual Dynamic Programming, GSDDP. Multi-Benders Decomposition, MBD, and sliding optimization. These algorithms, and others more existing in the literature, support the implementation of artificial brains. Electrical industries. Advanced analytics and optimization solutions across the enterprise. The image, produced by IBM, presents opportunities for optimization along the electricity supply chain. At the origin of mathematical models in computers, starting in 1947, decision support systems, which represent the optimization system of an electric company, were visualized as composed of multiple mathematical problems, one for each line of the diagram, which are operated individually and communicated sequentially by humans. This way of operating produces solutions close to the optimal, but not optimal, because they generally have no feedback. The current technological revolution completely changes this approach. Today, electricity business optimization can be visualized as a single supermodel, composed of submodels, which in turn are made up of mathematical problems, one for each line of the table, which are solved by running in parallel, autonomously, communicating with each other, and managed by a mathematical artificial intelligence, produced by a generative artificial intelligence. Hierarchical coordination of planning tools. It is traditional to organize decisions hierarchically into strategic, tactical and operational. The operational decisions are divided into the scheduling and advanced optimal control. However, due to the technological progress generated by Industry 4.0, mainly in relation to smart metering systems, nowadays we can talk about a new type of online optimization modeling, real-time distributed optimization. From the point of view of mathematical modeling, hierarchical levels are intertwined and coordinated through the boundary conditions in time, and common modeling that can be shared. The modeling strategy of HI is that all models of a decision support system can communicate with each other. Large-scale optimization and artificial brains. One of the fundamental ideas of the artificial brain is the atomization of the system, bottom-up approach, to integrate multiple mathematical models, using the framework of large-scale optimization methodologies, like multi-level Bender's theory, and Lagrangian relaxation. The same system can be organized hierarchically from multiple points of view. Because they are the same system, all these views must be equivalent. That is, in a non-degenerate optimization model, they have the same solution. The image presents the hierarchy from the point of view of regionalization. Considering the vision of large-scale optimization, which can have multiple points of view, HI developed the multi-Bender's decomposition, MBD, algorithm, to emulate the coordination of multiple points of view, just as the human brain does, following the studies carried out by Jeff Hawkins, summarized in his book, 1,000 Brains. On the other hand, if other intelligent structures are studied, different from the human brain, it can be concluded that this structure is not necessarily the best, and that there are alternatives in nature that can be artificially implemented. An example is the octopus, which has 9 brains, 3 hearts, and 2 memory systems, which it uses to control each of its 8 limbs independently, allowing it to move nimbly and react quickly to any threat. In addition, it has a central brain that hierarchically coordinates the secondary brains. This is one case, among several, of beings with multiple brains. It is evident that the structure of cephalopods is reproduced in human organizations, so a multi-brain artificial brain can be useful. In the global nature of modern companies, which must fulfill planning functions at different levels of their regional distribution for industrial, financial, and commercial operations, a multi-brain artificial brain structure is useful, as in cephalopods. Like the human brain, the artificial brain is made up of the following artificial components. Neocortex acts as an organizer of the connectivity of mathematical artificial neurons. Hypothalamus, it is the central processor that coordinates all the models included in an artificial brain, and hippocampus, it is the memory of the brain that stores the history of what is happening in terms of mathematical model runs. It is coordinated by a traditional artificial net. The most important planning function in a company may be integrated business planning, IBP, which integrates, at least, 3 areas: finance, marketing, and sales, and production. The IBP model can be looked at from 3 points of view. 3 independent models, which are integrated through a process in which the input of one model is the output of another. A monolithic model that integrates the three models, and that is run periodically, and an artificial hypothalamus that acts autonomously, in a distributed way, in real time. Power Enterprise-Wide Optimization System integrates mathematical models for each of electricity's supply chain links, so that supply chain planning is managed with a holistic view. Construction of artificial brains. The methodology for building an artificial brain follows a formal modular process, which High calls structured mathematical modeling. First, all mathematical equations, and their components, are stored in a relational database, part of an artificial hippocampus, which can be handled using SQL, standard query language. This implies an open and standardized structure, which is not common in mathematical modeling. Sets of constraints form problems, called by High, mathematical artificial neurons, and sets of problems form models, and a set of models forms an artificial hypothalamus, which is linked to the corresponding artificial cortex, a network of mathematical artificial neurons, and the artificial hippocampus, memory, which stores, in addition to mathematical formulations, the history of all model runs. From the concept of enterprise optimization, it evolved towards enterprise-wide optimization, which implies expanding the coverage of the decision support system, which High calls enterprise-wide optimization systems. Visually, it is easy to see the evolution of the IBP concept to EWOS, which covers all operational functions of an industrial organization. This leads us to two problems that must be solved from a computational point of view. If traditional approaches are used, many programmers are required to generate all the source code needed to develop and coordinate all models, and it takes a lot of computational power to solve the built-in problem. In order to solve this situation, High has developed OptX, Optimization Expert System, a generative artificial intelligence, which is responsible for producing all the source code required by an artificial brain, using large-scale optimization methodologies to solve complex high-dimensional problems. Electricity system and wholesale market mathematical models make up a flexible decision support system that provides different types of services in an integral way. They can be classified into integrated dispatch of generation plants, optimization of generating agents, and predictive analytics of stochastic processes. Traditionally, the optimization models in the electricity sector consider individual modeling with exogenous coordination between models, based on multi-stage stochastic programming, and using large-scale optimization methodologies. The differences with the state-of-the-art modeling, provided by High Power are integrated holistic modeling, scientific risk modeling, multidimensional uncertainty, parallel optimization, and autonomous real-time distributed optimization. Three types of connectivity of the generation system and the transmission power grid are considered. Ideal single node, ideal dispatch ignoring the transmission system. Electric transmission network connectivity based on the detailed connectivity of the electricity transmission system using bars and circuits. Operative areas connectivity, when the user does not have, or does not want to use, the detailed configuration of the electricity transmission grid. It is possible to use the connectivity based on operational area //app. Blaster online. com/speech low/changelogs including limits on the transfers between areas. Interconnection electricity, gas integrates electricity network with natural gas network. Interconnection of electricity and water can be fully detailed, including travel times between nodes and transport restrictions in water resource conduction channels. The central model of high power is the standard representation of the electricity and gas supply chains. These equations give rise to variations of the model according to the techno-economic concepts that support a specific modeling. There are at least 4 types of economic models to represent the electricity and gas market. Economic perfect dispatch, EED. Economic regulated dispatch, ERD. Nash-Carnot equilibrium dispatch, NCD, and unit commitment, UC. The EED is the core model of high power, as its equations/constraints are used in multiple specific models that the agent requires to address decision support needs. EED and the UC models optimize the dispatch of generation infrastructure, minimizing the cost of operating the electricity system, which simulates a perfect electricity market. The differences between these two models are the detail of modeling. EDD is oriented to planning and UC to real dispatch. Economic regulated dispatch, delivery of plants that minimizes the cost of operation of the interconnected system and includes representatives aspects of the regulatory of the electricity market being simulated. It does not correspond to a model of economic equilibrium, however, it is an easy and fast way to represent regulatory considerations based on optimization models. Nash-Carnot equilibrium, dispatch of plants oriented to the simulation of competitive electricity markets with agents that can influence with their decisions on transactions occurring in the market. It can be used to, among others, project the dispatch of a competitive market, and study the exercise of dominant market power of agents. Four models are considered fundamental to support the strategic, tactical and operational decisions of an agent that operates generation plants. The diagram presents the design of an integrated set of mathematical models to support the decision-making of a generator agent. Electricity dispatch and financial analysis. Integration dispatch models with assets liabilities management, ALM, financial models including risk management, to perform analysis of the financial impact of decisions. The main applications are the valuation of income and expenses of investment projects, energy installations, and valuation of energy companies, and integrated optimization of investments by global energy companies, taking as a reference the regulatory laws of the different regions or countries. The financial modeling results individualize the operating income and expenses, and can include all types of legal accounts. Electricity supply chain design and risk management, associated with strategic planning decisions related to resilient design of supply chain, in relation to capacity of reservoir, transfers, power plants and other assets of an electrical system. It may include risk management and financial planning. Energy trading and risk management. Optimal decisions related to trade energy and coverage of financial risks based on standardized or no bilateral contracts. It corresponds to a set of mathematical models aimed at supporting the decisions of the different agents involved in energy trading in long-term market, spot market, and secondary markets. The result of a risk analysis is the definition of Pareto curves of risk versus expected revenue, based on which the decision maker must define the risk position he wishes to assume, varying between risk-prone and risk-averse. Maintenance optimization is oriented policy making preventive maintenance of multiple central generation plants and others electrical assets. It can be applied to all assets in a regional or national grid. High power man can be implemented following the principles of PHM, prognostics health management, for industrial asset maintenance, integrating specific models of predictive analytics for asset components and prescriptive analytics to optimize the integrated operation of the asset network. High power has been used by ISO in Peru, and Market Supervisor, in Colombia, for planning and decision-making purposes. High power includes some predictive analytics models. Spot price modeling. The prediction of spot prices of the energy market is fundamental for the decisions made by an agent that participates in that market, whether buyer or seller, generator, trader, or distributor of energy. This is because the decision maker requires that the model's results that produce spot prices be used in other mathematical prescriptive models. The mathematical models to be used depend on the planning period, short, medium or long term, and the type of market considering the dispatch of the plants, by mathematical model, or by market agents offers in a free market. In free markets the situation is complex since the law of price formation cannot always be explained based on mathematical rules, explicit, clear and universal, that may integrate a mathematical model. Synthetic generation renewable energy sources. For the generation of synthetic scenarios of climate variables, there are two requirements: short-term, hours, days, and medium/long-term, weeks, months. Specific short-term models must be built for each renewable source. For the medium and long-term, there are three alternatives to generate synthetic scenarios. Synthetic statistical model for the generation of climatic variables, firing Metalis type. Generate synthetic series of climatic variables based on the mixture of historical series. Generate synthetic series based on the historical series having the ENSO series, El Niño Southern Oscillation, as an instrumental variable. Projected short-term hydrological contributions using variations and enhancements of Kalman filter. All Power L models share the same data model, input and output, in such a way that communication between models is direct. In the same way all models make up the artificial hypothalamus of the wholesale market of the electricity sector. Smart grids optimization models. In a regulated environment, generation, transmission, and distribution are operated by a vertically integrated enterprise, usually a state-owned, which has a monopoly on the supply of electricity. Conversely, in a deregulated environment, different parts of the electricity grid are owned and operated by different actors, and electricity markets provide a platform that fosters competition among participants. As each smart grid it requires a specific decision support system that allows the operator to interact with the entire electrical system. HiSGO provides all the analytical elements necessary to configure the specific DSS that each case requires. HiSGO is composed of forecasting models and optimization models aimed at supporting the decision-making of electric agent smart grids, optimization of the economic and technical aspects related to smart grids and electricity companies. Demand response for buildings and housing, demand response, optimization of energy management in facilities, such as universities, shopping centers, and industrial energy efficiency, optimization of energy management in heavy industries intensive in energy consumption. Forecast renewable energy sources. They correspond to predictive analytics models focused on the prediction in the specific sites where are located the generation plants. Forecast of demand energy. Demand projections per years, months, weeks, days, hours. HiSGO is integrated by the following optimization models. Economic dispatch of the smart grid, optimization of the management of electrical energy in small cities, factories, universities, shopping centers, office buildings, urbanizations. Smart grid unit commitment, optimization of the dispatch of the electrical load in real time, or in the short term. Smart grid configuration, optimizing the network topology. It considers voltage control, configuration of feeders, location or activation or reallocation of electrical assets, like transformers, capacitors, and phase balancing. Smart grid design, optimization of the design or redesign of smart grids with modern power technologies. ETRM, electricity trading and risk management, decisions to buy and or sell electricity, in a long, medium and short-term market, one day in advance or the day of dispatch. Industrial energy efficiency. The technical economic viability of energy storage coupled with the proliferation of energy technologies based on renewable energy sources has changed the landscape of the industrial sector, since it is now possible, and increasingly efficient, to generate renewable energy and store it for use in due time. In practice, all industrial companies can be agents that interact in the electricity market acting as co-generators and carry out commercial activities and transactions. This, together with the industrial Internet of Things, increases the pathways to achieve industrial energy efficiency. Industrial energy efficiency results of the integration of production processes, transformation of matter, with industrial energy services, energy transformation, aimed at the simultaneous optimization of both industrial production and energy conversion that is related to polluting emissions of gases and liquids, associated with increasingly demanding environmental control laws. The high-power and HiSGO models can be integrated with complex industrial process models, in which it is necessary to redesign the power supply system according to the new power technologies. This type of model includes the simulation of polluting processes, for example, combustion in furnaces, to determine the optimal mixture of fuels in accordance with environmental regulations. High power and HiSGO integrate the models and information systems around a common data model, allowing models to be connected automatically through the database or through RAM memory, integrating them as an artificial hypothalamus for an electricity company of wide coverage. For more information you can write to the email that appears on the screen. Alfred North Whitehead affirmed, "Algebra is the intellectual instrument which has been created for rendering clear the quantitative aspects of the world." The importance of this phrase lies in the fact that all modern mathematics is based on algebraic models that become algorithms, that use all the power of current computer technologies. Thank you for your attention.